discussing about the self-inductances. Now here we are given two coils. So self-inductance is defined as the property of the coil to oppose any change in current that is flowing through it. It is opposed by inducing an EMF that opposes that change in current. In case number 1, we see that here the current is increasing, so the EMF or a back EMF is produced in this coil that opposes the increasing current. In this case, the current is decreasing, so a back EMF is produced in this coil to oppose this decreasing current. And this property by which the coil opposes the change in current, either decrease or increase by inducing an EMF in that coil, in the same coil, is called as self-inductance. Now, we know that if phi is the flux produced, phi is directly proportional to the current, I. If the current is more, the flux produced is more. So, phi is equal to Li, where L is the constant of proportionality, and that constant of proportionality is called as coefficient of self-inductance. Now we know that the EMF is produced and is directly proportional to the rate of change of the current di by dt. Here also the constant of proportionality is the coefficient of self-inductance, that is L, but we introduce a negative sign. The negative sign shows that this back EMF opposes the change in current through it. So we have E is equal to minus L di by dt, where L is the coefficient of self-inductance and di by dt is the rate of change of current. Now let us define L. We know that from this equation phi is equal to Li, phi is equal to Li. So if I is equal to 1, so phi is equal to L. So we have the coefficient of mutual inductance is numerically equal to the flux produced in the coil when the current flowing through that coil is equal to 1 ampere or 1 unit. Now also taking the magnitude of E, that is L di divided by dt. Here if we have di by dt is equal to 1 unit, in that case E will be equal to L. So we can define the coefficient of self-inductance as numerically equal to the EMF produced in the coil if the rate of change of current through that coil is 1 unit. Now going to the units and dimensions of this L. Now we have that L is equal to phi divided by I. We know that the units of phi are Weber and units of current are ampere. So the units of L are Weber per ampere. And this SI unit, Weber per ampere, is called as Henry. So we can have that 1 Henry is equal to 1 Weber per ampere. Now also from this equation E is equal to L di by dt, we have that L is equal to E divided by di by dt. Now we know that the SI unit of EMF is volts and current is ampere, time is second. So the SI unit comes out to be volt second per ampere, and this volt second per ampere is also called as Henry. So we can define the self-inductance of a coil as 1 Henry when the EMF produced in the coil is 1 volt by the change of current. That change of current is 1 ampere per second. Talking of the dimensions of L. Now we have L, the units of L are volts second per ampere. We know that the EMF or voltage whose SI unit is volts is work done per unit charge. That work done per unit charge has got dimensions of mL2 t minus 2 divided by AT, because current is charge per unit time, charge is current into time divided by ampere. T and T goes, this A comes to the denominator, so that is mL2 t minus 2 divided by A2. This A raised power 2 comes into the numerator, so the dimensions of L are mL2 t minus 2 A minus 2. These are the dimensions of the coefficient of self-inductance, whose units, SI units is Henry, and the dimensions are mL2 t minus 2 A minus 2. Thank you.